Hello, everyone. Today, for our video lecture for Unit 3, we're going to talk about the models of the atom as they were developed throughout history. So we're going to talk about the scientists that were responsible, the experiments that they performed, and then how the model of the atom kind of improved to what we know it is today. There is going to be some years that are associated with this. Don't worry too much. I just kind of use those as a frame of reference to see how long or how short the time span was until they improved upon the model. So this won't turn into like a history test where you need to talk about like what year was this model developed. Don't worry too much about that. Okay, so we're going to start all the way at the beginning, as all good stories do. And the year 460 to 370 BC, there was a Greek scientist. His name was Democritus, and he had this theory that everything that is made up of matter is composed of atoms. And his idea was that if you take a sample of matter and you cut it down into smaller and smaller pieces, eventually you're going to get to the smallest indivisible piece. And those individual little tiny pieces he called atoms because the Greek word for indivisible is atomos. And so this model is a pretty simplistic model, but he just thought that all atoms were these tiny little spheres, and that all these little tiny spheres came together in some way to make up all matter in existence. Right? It wasn't until several thousand years later that John Dalton improved a little bit, added more to Democritus's theory of the atom, and said that if you have atoms from the same element, like multiple atoms from a bar of gold, all of those atoms are going to have similar properties, similar size, similar mass. And if you were to compare those atoms to then, say, atoms from a bar of silver, those different atoms are going to be different sizes and different masses. So John Dalton's model didn't really change much, but he added to this idea that atoms can be slightly different based on what they're composed of, right? It wasn't until about 50 years later that J.J. Thomson discovered the existence of the first, what we call a subatomic particle, meaning below the atomic level, pieces that build together to make up atoms, even smaller than atoms. And so this first subatomic particle that was developed, or not developed, discovered, was the electron. And his experiment is called the cathode ray tube. And I've got a little video here that's going to be a good visualization of this cathode ray tube experiment. And so on the screen before you is a cathode ray tube. It's a vacuum tube that on either end there are these metal electrodes that are sticking off of it. So eventually when I hit play, this guy that ran this video is going to have electricity running through the center of that tube. And you're going to see a beam of light, this green light that shows where these electrons are being transferred from one end of the tube to the other in front of this like white screen backdrop. Okay? So here we see that green beam, and it's kind of faint. And if you notice in the bottom left corner of your screen, there's this little metal rectangle. He's got a bar magnet. And you probably played around with magnets before. You know that like the two negative ends repel off of each other, and then the opposite ends attract to one another. And this is what Thomson did. He took a magnet next to this cathode ray tube and realized that the negative end of the magnet pushed the beam away, and that if you flip it around, the positive end of the magnet is going to attract the beam towards the magnet. So here he switches it to the positive end, and now the beam starts to bend towards the magnet. So this simple experiment led Thomson to understand that there must be something negatively charged if it's repelling away from the negative end and attracting to the positive end. So the electron gets its name because it was derived using electricity, but the charge of all electrons are negative, right? So Thomson's model has now added to the fact that these small atoms are also structurally made up of little tiny negative pieces. Those are minus signs or little negative signs. And the term for this model is called the plum pudding model. And the real reason for that is that Thomson was a British scientist, and they have desserts in Britain called puddings, which are essentially a cake. And if you make a plum cake, the plums are going to be like scattered throughout all over the place randomly in disorder. So that was his theory, was that these electrons are just kind of scattered randomly about the inside of an atom. Okay? A couple decades later, Ernest Rutherford did another experiment proving the existence of the next subatomic particle, the proton. And this experiment is what we call the gold foil experiment. And so I wanted to show you the next video clip here. Ernest Rutherford's gold foil experiment utilized radioactive material. And so at the same time, while this experiment was being done, they knew that this radioactive material were these little tiny positive radioactive particles. And so they used this blue box to essentially shoot radiation through this open silver square, which has a circle in it, kind of like the aperture on a camera. And they expected these radioactive particles to just fly clean through that yellow square of gold foil. And then this green screen was a way for them to detect where that radioactive material hit. And they realized that every once in a while, these particles would pass clean through it, meaning that the atom is made up of a lot of empty space. But then also it could hit the center of the atom head on, and like two positives repelling each other, they might they might repel. And so Ernest Rutherford's experiment proved the existence that protons are a part of the atom and that they have to be positively charged. There's got to be something positively charged because positive radioactive material is also scattering about when it comes into contact with each of these atoms. Okay? And so Ernest Rutherford's model said that we've got this smaller positive core, because not all of the positive radioactive material was deflected, some of it passed through. And this is the most common visual of an atom that you've seen before. And this is what we call the planetary model. Basically, he said that, yeah, those electrons still exist, but now they're in these orbits, and they kind of orbit around that positive proton core. So Niels Bohr improved upon the planetary model and said that these electrons are able to transition between what we call energy levels or shells. Think about like a ball or a golf ball within a tennis ball, within a softball, within a basketball. So these spheres get larger and larger as they go through. So the model for Bohr's atom is that there still is the nucleus at the core, and that these electrons exist in these shells that get larger and larger the further away you get from the nucleus. And so this is getting closer to what we know today as the model of the atom. But the last scientist that put the final touches on this atomic model is a guy by the name of Erwin Schrödinger. And he took a lot of math, some really advanced mathematics, and realized that you could figure out the probability of where these electrons were located. And this is the first kind of beginnings to the fields of quantum mechanics. Now, we are not going to touch anything in the world of quantum mechanics, but it is important to know this is like the truest structural format of what we call the model of the atom. And that is now that in our nucleus, we've got protons and neutrons. Right? So we've got this packing material, neutrons in the middle with all those protons. And then the electrons are going to exist in these probable energy levels outside the nucleus. Right? So we've got electrons that can exist in either spot. And it's possible that these electrons could transfer from one orbital to the other. But the biggest key piece to this final model is that all of this space between these energy levels is completely empty. A majority of all atoms take up little to no physical space. It's just open, empty space between the electron energy levels and the nucleus.